Hello and welcome to this lecture on advanced electric drives. In the last lecture, we are discussing about the direct torque control of induction motor, and we have seen that in direct torque control, the torque and flux are compared into hysteresis comparator, and the torque and flux status are generated. And this torque and flux status are used to switch the voltage source inverter, which ultimately feeds the induction motor. Now, we also know that whenever we have a VSI, we have 8 possible switching states, and out of the 8 possible switching states, 6 are non-zero switching vectors and 2 are zero switching vectors. And in direct torque control, we have to select one of these 8 switching vectors so that we can fulfill the torque and the flux status. Now, we will just discuss how to find out the switching vector from the torque and flux status. So, we will draw a lookup table and we will fill up the lookup table based on the various voltage vectors that we have for a 3-phase 2-level voltage source inverter. So, we are drawing now the lookup table for switching voltage vectors. Now, what we have 6 different sextets. So, this is the lookup table we have. And in this case, we have 6 different sectors. So, this is our sector 1, this sector 2, sector 3, sector 4, sector 5 and sector 6. These are the sectors. And then we also have the torque and flux status. So, this is the status. And what are the status? Here we have d psi equal to 1 and d psi equal to 0. D psi equal to 1 means the flux will be increased, and d psi equal to 0 means the flux will be reduced or decreased. And corresponding to one flux status, we can have 3 possible torque status, because we know that the torque hysteresis comparator is a 3-level hysteresis comparator. So, we will have 3 different torque status. The torque will be increased, torque will not be changed, and torque will be decreased. So, we have dm equal to plus 1, dm equal to 0 and dm equal to minus 1. So, we have 3 different torque status: dm equal to 1, dm equal to 0 and dm equal to minus 1. And similarly, here also we can have 3 possible torque status: dm equal to 1, dm equal to 0 and dm equal to minus 1. Now, we have to find out the voltage vector which will fulfill this 3-phase VSI and we have 8 possible voltage vectors, and the voltage vectors are V1 to V6 are the non-zero voltage vectors, V0 and V7 are the zero voltage vectors. So we can draw them once again. This is V1, and then we have V2, V3, V4, V5, V6. And then we have the zero voltage vector V7, and V0 is also a zero voltage vector. And if we also show the switching status, we can show which switches are on for V1. We can show V1 as plus minus minus. Similarly, V2 as plus plus minus. Plus minus minus means phase A upper switch is on, phase B lower switch and phase C lower switches are on. Similarly, the plus signify the upper switch being on, and minus signify the corresponding phase lower switch is on. And similarly, we can write for V3, V3 is minus plus minus, and V4 is opposite of V1, that is minus plus plus, and V5 is opposite of V2, that is minus minus plus, V6 is opposite of V3, that is plus minus plus, and V7 is plus plus plus, V0 is minus minus and minus. So we have 8 voltage vectors, and we can divide the whole space into 6 sectors, and each sector will be having an angle of 60 degree. Each sector is equal, so we can divide this whole space into 6 different sectors in the following fashion. So we can call this as sector 1, and this is sector 2, and this angle is 60 degree. Similarly, all the sector angles will be 60 degree. This would be sector 3, this sector 4, sector 5, this sector 6. And the objective here is that we have to find out the suitable voltage vector which will fulfill the torque status and the flux status simultaneously. So let us say that our original flux vector is in sector 1. So we can say that, say for example, our flux vector is here. This is psi s at t equal to 0. And we know that we have equation that we have already seen in the last lecture, that psi s, the resultant flux vector, is given as integral of Vs dt 0 to delta t, let us say, plus psi s at t equal to 0. So it means if we want to find out the resultant flux vector, we have to apply a particular voltage vector, that is Vs. Now if Vs is kept constant for a time, that is delta t, so we can write this equation as Vs into delta t plus psi s at t equal to 0. So this is a vector equation, and the resultant vector is psi s, and psi s is the vector sum of Vs into delta t and psi s at t equal to 0. So here let us say that our flux vector at t equal to 0 is in sector 1, and what we have to do here is that we have to increase the torque and increase the flux, dm equal to 1 and d psi equal to 1. So if we take this situation that dm equal to 1 and d psi equal to 1, It means both the torque has to be increased and flux has to be increased. So, if we see this diagram here, now which vector shall we apply? Shall we apply V1? Now, if we apply V1, then the vector will be moving in this direction. That is not correct, because if you apply V1, the torque will be reduced up to some extent, will not be increased, but we have to increase both the torque and flux. So, what we will do here is the following. Maybe this is not the right choice. We will apply V2. Now, if we apply V2 in this case, this is our V2 into delta t. We will apply V2 for a small time delta t, and as a result, our resultant flux vector will be along this direction. So, this is psi s. So, we see that psi s has moved. When the psi s has moved, gamma has changed. Gamma is the angle between psi r and psi s. Gamma psi r, the rotor flux may be somewhere here. So, for example, this could be the position of the rotor flux vector. So, the gamma has changed instantaneously, and when gamma has changed instantaneously, gamma has increased, sine of gamma has also increased, the torque has also increased. So, we have fulfilled the torque status. Torque has to be increased. Now, what about the flux status? Now, we can see that here, when we are applying this voltage vector, psi s seems to be greater than psi s at t equal to 0. So, in this case, the flux has also increased. So, we have satisfied both the torque status and the flux status. So, here what we will do in this case is that we will say that here we have to apply V2. Okay. And then if you come to the next condition under this sector 1 theta 1, that d psi equal to 1 and dm equal to 0. The flux has to be increased, but the torque should be maintained as it is. Now, if you see this equation, if we want to maintain the torque, gamma should not be changed. So, gamma is the angle. What is gamma here? Gamma is the angle between the rotor flux and the stator flux. This is our gamma. And if we do not want to increase gamma, we have to freeze the stator flux vector. The flux vector should not be accelerated, neither it should be decelerated. Angle at that instant should be as it is, it will be held constant. And if you want to hold that angle constant, you have to apply a 0 voltage vector. It means in this equation, if suppose Vs is equal to 0, then psi s equal to psi s at t equal to 0. So, the flux does not change. The position of the flux vector also does not change. So, if you put Vs equal to 0, or if you apply a 0 voltage vector, the flux vector is frozen, and hence torque neither increases nor decreases. What about the flux then? Now, when we have two status, flux status and torque status, the torque status will have higher parity compared to the flux status, because ultimately in a drive what we want is that the torque should be controlled. Flux should also be controlled, but if you see the priority, the torque at a given time should be given more priority than the flux, and we know that flux cannot change instantaneously. Flux will take some time to change. So, we can give a lower priority to the flux, and we can fulfill the torque requirement. So, in this case, you know that if you apply a voltage vector that is equal to 0, so what we can say is that this component vanishes. So, if that vanishes, you know that psi s equal to psi s at t equal to 0. So, if psi s is kept as it is, it means the torque does not increase nor it decrease. What about the flux? Flux also does not change, because we are not increasing the flux nor we are decreasing the flux. So, the flux is maintained at that particular value. So, in this case we will apply in this case a 0 voltage vector. So, if you see that the voltage vector here will be V7. We have the choice to apply either V0 or V7. We have two 0 voltage vector, V7 and V0, and we have applied V2 little earlier because we wanted to increase the torque and increase the flux. Now we want to keep the torque as it is. So, from V2 it's easier to switch to V7 than V0, because V2 is plus plus minus, and if you switch to V7, it is plus plus plus. So there is a change of only the switches of one leg, that is the C phase, the upper switch is turned on and the lower switch is turned off. So what we say here, to avoid the minimum number of switching, we will have V7 here. And then the third row here, the flux d psi equal to 1 and dm equal to minus 1, means flux should be increased, torque should be decreased. Now if we see here, we have the flux vector which is in the sector 1, and we have to increase the flux but decrease the torque. So gamma has to be reduced. It means the flux vector should be decelerated, but the magnitude should be increased. So we will apply such a voltage vector which will make gamma small. So in this case, you know that we have a choice to apply V6. Now if we apply V6, suppose we apply V6, so V6 will be in this direction, and this is V6 into delta t. We are only applying for a small time delta t, because the whole interval has been broken down into small sampling time, and the sampling time is delta t. So in this case, if you apply this V6 for delta t, the vector will be moving in this direction. This is the vector, that is V6 into delta t, and the resultant of the two would be, and here what we see here, that results in a reduction of gamma, but the flux has increased, the magnitude of the flux has increased, but the gamma has reduced. So the flux is increased but the torque is reduced. So we can say in this case that here we will apply V6. Now similarly, when the flux status is 0, d psi is equal to 0, we want to increase the torque, dm equal to 1. It means the flux should be reduced but the torque should be increased. So we will apply, in this case, I mean we have the vector which is in sector 1, and we want to reduce the torque but reduce the flux but increase the torque. So we will apply in this case V3. So if we apply V3, we have the flux changing like this. So when it is changing like this, the resultant of these two will have a reduced flux, but since gamma has increased, the flux vector has moved in the anticlockwise direction, gamma has increased, and hence instantaneously we will experience an increase in the torque. However, application of V3 will reduce the flux up to some extent. So we are able to satisfy increase of flux but increase of torque but decrease of flux. Of course, the reduction in the flux is not significant, because we are not applying a voltage vector to fully demagnetize the flux. We are applying a voltage vector in such a way that some component of the voltage vector will be opposing the stator flux. So flux reduction will not be by a significant amount, but however that will be enough to satisfy the flux status. The flux is reduced but the torque is instantaneously increased, because gamma angle, the angle between the rotor flux and the stator flux, is momentarily increased, and hence we experience an increase in the torque. So we will apply in this case V3. So this is what is V3 here. We are applying V3. So to increase the torque and decrease the flux, we will apply V3. And then to decrease the flux and keeping the torque unchanged, we will apply V0 similarly, because from V3 it is easier to come to V0, because if you see this, V3 is minus plus minus. So from minus plus minus, it is easier to come back to minus minus minus. Only B phase upper switch will be switched off and the lower switch will be switched on. So it is easier to move from V3 to V0 than from V3 to V7. So in this case, in the lookup table, we will have V0 here. And then the last row, the torque should be decreased, dm equal to minus 1, and the flux is 0. Flux should also be reduced. So if the flux is reduced and torque is reduced, we will see which one is most appropriate. Both are to be reduced. So if both are to be reduced, which vector shall we apply? We can apply in this case V5. Now if you apply V5, the vector will be moving in this direction. So we have a reduction in gamma, also reduction in the magnitude of the flux. The resultant in this case will be somewhere here, and this will lead to a reduction in the flux magnitude as well as reduction in the angle gamma, which is the angle between the stator flux and the rotor flux. So we satisfy both the flux and the torque status. So we will have here, this is V5. Similarly, we can find out by the same logic the switching vectors in sector 2, sector 3 up to sector 6, and since they are symmetrical, we can just write down out of symmetry, this is V3, V2, V3, this is V4, V5, V6 and V1, and this will be V0, then V7, V0, V7 and V0, and out of symmetry this is V6, V1, V2, V3, V4 and V5, and here this is V3, and out of symmetry this will be V4, and this will be V5, V6, V1 and this is V2. So since the sectors are identical, we can write down out of symmetry because we have V1, V2, V3 in the anticlockwise direction. So the sequence is V1 to V6, and this 0 vectors will alternate because it is easier to switch to V7 from one vector, and it will be easier to switch to V0 from the other vector. So we can similarly do here V7. It is easier to switch from V4 to V7. What is V4? If you see that V4 is minus plus plus, so we can easily move to V7, that is plus 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 from minus plus plus. So from V4 we can go to V7. Similarly from V5 we can go to V0. Then from V6 it is easier to move to V7. From V1 it is easier to move to V0. From V2 it is easier to move to V7. So this is how the vectors are changed. And similarly the last row we can have V5, then V6, then V1, V2, V3 and V4. This is out of symmetry, we can write down all the voltage vectors. So this is basically our switching lookup table. It means if we know the sector information of the flux, and if we know the torque status and flux status, we can uniquely find out one voltage vector that simultaneously fulfills the torque status and flux status for the direct torque control of induction motor. Now it is very easy to implement in the sense that we don't have to have much computation here. At base what we have to do is to find out the flux sector information theta, and once the theta is available and by means of a comparator we can compare the reference flux and the actual flux and have a flux status. Similarly we can compare the reference torque with the actual torque and have a torque status, and from the lookup table we can select which vector is the most appropriate vector, and if we apply that particular vector, the torque and the flux status for the induction motor will be fulfilled. Now this we can show in form of a block diagram. Our objective here is that we should be having a variable speed drive where the speed is controlled. We have to control the speed very smoothly, and for a variable speed drive we can draw a block diagram using the direct torque control principle. So this is our block diagram. Now, here we are actually employing a voltage source inverter. Our machine is fed from a voltage source inverter. So, that is what we will show here, and we will have actually the reference speed, and we can compare this with the actual speed. And then we can feed it to a PI controller. And usually the speed error is fed to a PI controller, and the PI controller gives us the reference torque. It means if the error is more, we should be needing more torque for the acceleration. If the error is positive, the actual speed is less than the reference speed, so we should be having more and more torque. So, the PI controller output is basically the torque reference. So, this is TE star. And this is what we compare with the actual torque. And then, as we have already discussed, this is fed to a 3-level hysteresis comparator, and out of this what we obtain is the torque status. Similarly, in case of the flux, we can give the reference flux, and we compare this with the actual flux. And then what we do here, we feed it to again a 2-level hysteresis flux comparator, and the output of that is the flux status, that is d psi. And then we have the switching lookup table, and we have the VSI. Inverter and control. This feeds the induction motor. And we have, let us say, a speed sensor or a tacho generator. Out of this, we obtain the speed feedback. So, speed is fed here. We have omega r in this case, and this is the omega r which is obtained here, and we can feed this omega r to have closed loop speed control. Now, the switching lookup table also requires information about theta. Theta is the sector information. Whether the flux vector is in sector 1 or sector 2 or in sector 3 up to 6, unless we have that information, we cannot uniquely find out the voltage vector which has to be applied on the machine. So, we have to find out the sector information. And how do we find out the sector information? We can find out the sector information from a calculator block, that is torque and flux estimator. And here in the estimator, we feed in this case VDS, VQS, IDS and IQS. And this is our induction motor, and these are the various currents here, IA, IB, IC. And the switching lookup table will be giving the signal for 6 switches. The inverter will have 6 switches. So these are the 2 switches of phase A, 2 switches of phase B, and 2 switches for phase C. And the inverter will be fed from a DC source. This is our VDC. It's a voltage source inverter. So we have to have a DC supply which can be obtained by means of a rectifier as well. So this DC supply will be the input to the inverter, and the inverter will be controlled by these signals that has been obtained from the switching lookup table, depending upon which vector is to be applied. So we have 6 driving signal, the gate driving signal for the switches of the inverter, which are fed to the inverter for turning on and turning off of the 6 switches. And then the output is fed to the induction motor. And of course, what we need to do here is that we have to have a sensor. We have to have some sensor to sense the currents and the voltages, because in this case we need VDS. How do you obtain VDS? Now VDS is a stationary reference frame current that can be obtained from the output VA, VB, VC. Of course, in this case what we have here is phase A, phase B, and phase C. We can have Hall sensors here to measure the line voltages, and from that we can calculate what is VDS and VQS. And similarly, we can have the current sensors here, and this current sensors will give us IA and IB, and from IA and IB we can find out what is IDS and IQS in the stationary frame. We don't have to have any rotating transformation, because these variables are being calculated in the stationary frame. And these are the input to this torque and flux estimator, and this output of the torque and flux estimator will be TE, the torque, and the stator flux is respectively. The TE will be fed to the torque comparator, and the flux will be fed to the flux comparator. And out of this also we can obtain the information about theta, and the theta information can be used to find out the sector. Now we can have a mathematical expression for this torque and flux estimator. We can write down a few equations which will tell us how do we estimate the flux and the torque of an induction machine. So we can write down the expressions for flux and torque estimation. So we have a simple integrator here for finding out psi ds, that's equal to VDS minus RS IDS dt. Simple integrator will tell us what is psi ds, and similarly we can calculate what is psi qs, integration of VQS minus RS IQS. And then what is psi s? Psi s is the square root of psi ds square plus psi qs square. So we have been able to find out the amplitude of psi s, which will be used for the feedback. What about the sector information? The sector information can be calculated. Theta is equal to tan inverse of psi qs by psi ds, because we know in this case this is our psi s and this component is psi ds, the stationary reference frame components, and then this will be psi qs and this angle is theta. So we can take simple tan inverse of psi qs by psi ds, and that will be our angle theta. And then what about the torque? The torque can be estimated TE is equal to 3 by 2 into P by 2. We have psi ds, we have been able to calculate psi ds, into IQS. IQS we can always measure using a Hall sensor, minus psi qs into IDS. So this is the expression for the torque, and this expression for the torque can be obtained from the flux and the current. The flux is calculated and the currents are measured. IDS and IQS are measured. So this torque can be used for the feedback here, because we have a torque feedback, and similarly the flux which is calculated is also fed back here, and angle theta is used for the computation of the sector. And when we know the torque status and the flux status and the sector information, we can find out which vector has to be applied. And once we apply that particular vector, the flux and the torque status are fulfilled and the motor is controlled using the direct torque control. So this concludes our discussion on direct torque control of induction motor. We have already discussed the control of induction motor drives, and the induction motors are very widely used in the industry. About 70 to 80% of the motors used in industries are induction motors. We will also be discussing about the control of synchronous motors. Synchronous motors are used for high power applications. They are not used for low and medium power applications. They are used for very high power application, ranging from a few megawatts to tens of megawatts, maybe up to 100 megawatt also in certain application, for a very huge drive. But usually these motors, the synchronous motors, are used for rating higher than 1 megawatt. So we will be discussing about the control of synchronous motors. Synchronous motors can be controlled in two different ways. The first one is called the control with true synchronous mode, and the second one is called a self control mode. Now we will be discussing this one by one. Let us first concentrate on true synchronous mode of control. Now in true synchronous mode, what happens is that the motor is fed from a voltage supply of independent frequency. Say for example, a synchronous machine connected to an infinite bus. That is an example of a synchronous machine operated in true synchronous mode. And in many applications like fixed speed application, where the speed is not variable, true synchronous modes is sufficient. We don't have to control the speed, the frequency is constant, and the frequency is independent of the speed, and the motor speed remains constant. However, the true synchronous mode is not very suitable for variable speed application. So in true synchronous mode, the motor is supplied from a voltage source of independent frequency. Now what is the drawback? The drawback is that whenever we are connecting a synchronous motor to a voltage source of independent frequency, there is a question of stability. And you know that in the transient condition there could be hunting. Synchronous motors should be running at synchronous speed. If the synchronous speed does not match with the rotor speed, there is a transient oscillations. And sometimes if we have a large transient, the machine may also fall out of step. That may also become unstable. So the difficulty in this case is that the motor may be unstable, motor may exhibit hunting. So the disadvantage here motor may exhibit hunting. Can be unstable for large transients. La transients means suppose we apply a very high load which is applied and the motor may fall out of step. Furthermore, suppose we want to increase the frequency of the supply and we increase from, let us say, 25 hertz to 50 hertz immediately. The motor may not be able to respond to such a large change of frequency. So it may fall out of step. So these are the inherent problems of motors operating with true synchronous mode. However, if we are talking about a fixed speed application, this is one of the ways we can feed a synchronous machine. In some situations where the speed response is not a big constraint, what is done actually, the frequency of the supply is not changed in step, it is changed slowly. And the machine, the rotor being a mechanical entity that can respond to a slow change of frequency. So instead of applying a step change of the frequency, one can apply very slow change of frequency and the motor may respond to the slow change of frequency and the speed may gradually vary. So we will see an example of how we can control a synchronous machine with true synchronous mode. So let us say we have a rectifier here. The rectifier may be a 3-phase rectifier and then we may have a small filter and then we can have a VSI and we can connect one or multiple motors. These are synchronous machines. And then we need to control the frequency of the voltage source inverter and that is basically controlled slowly. So we have a frequency command here, a star, and this is connected to a delay block. So there is a delay here, we can have delay circuit. And then this delay circuit will be giving a frequency which is fed to the VSI. The VSI can be a sine wave VSI, it can be a sine PWM VSI and it will be applying a 3-phase voltage to the stator of the synchronous motors and the frequency, the fundamental frequency being F and F is changed slowly. And then as F is changed, this could be a control rectifier. We can use here a control rectifier. I mean, instead of a diode bridge rectifier, if we want to change the voltage here, it can be a controlled rectifier. And then we know that as we change the frequency, we also have to change the voltage. So here we change the voltage to keep approximately the V by F constant. So here we have function generator which will be generating the amplitude of the voltage, that is V star, and then we have a triggering circuit which will be generating alpha. So this alpha is the triggering angle of the rectifier, and if you want to increase the voltage, we reduce alpha and the DC voltage goes up, and then this DC voltage is VDC. It could be a semi-controlled rectifier to keep this DC voltage in the same polarity, and then we have a VSI which feeds the synchronous motor. So this frequency change here, F, is not very abrupt. Because of the delay circuit here, the frequency change is gradual. But this cannot be used for very high performance drive system because we cannot change the speed immediately. So we have to have a mechanism of changing the speed starting from 0 to the full speed with good dynamic response. So we go for what is called a self-controlled mode. So we will see actually what is a self-controlled mode. In this case, the stator frequency is not independent of the rotor frequency or the rotor speed. The stator frequency is decided by the rotor speed. It means the motor is controlling itself. Synchronous motor is always synchronized with the rotor. So it means the rotor is controlling the stator frequency, and hence it is called self-control mode. So we can say here that the stator frequency is decided by the rotor speed. Hence, there is a rotor position feedback. So in case of a self-controlled drive, synchronous motor drive, there has to be a rotor position feedback. Unless we have a position feedback, the stator cannot be synchronized with the rotor, and hence all self-controlled drive should have a rotor position feedback. And the advantage here is that we don't have any hunting, we don't have any instability. A self-controlled drive cannot be unstable in a sense that it cannot fall out of step, because the stator frequency is being decided by the rotor, so it cannot fall out of step with respect to this rotor. And similarly, there is no question of hunting here, because the rotor frequency and the stator frequency are locked together. So the hunting is also prevented here. So the advantage in this case is this, that hunting is prevented does not fall out of step. And also one big advantage is that this kind of drive can be employed for variable speed application, because the frequency can be varied, there is no fear of losing the synchronism, and hence we can operate starting from 0 speed to the full speed. Can be applied for variable speed application. So we will take an example of a synchronous motor drive which is self-controlled, and we will see how we can control this and how we can control this with variable speed application. So let us take an example of a CSI fed synchronous motor drive. Now CSIs are basically used for high power application, and this drive is suitable for high power application. So what we have a CSI which is being fed from a control rectifier, and in the DC link we have a large inductor to keep the current constant. So we have here a control rectifier, and these are 3-phase supply. Then in the DC link we have a large inductor to keep the current constant, and then we have a CSI, and the CSI is feeding the synchronous motor. A synchronous motor of course will be having a position sensor. So we can use here encoder or a resolver which will be giving us the information about theta r. Theta r is the rotor position, the position of the rotor. And then the CSI is, this is our CSI, and this is the converter or the control rectifier, and this is VR, and this is VI, and this is the DC link. We have a large choke here, and this choke is having a resistance of RDC, and this is II, the current which is being supplied from the converter to the inverter. So, we can call this to be the inverter input current II, and here in the synchronous machine we have three different phases. So, we have IA, IB and IC, and this CSI or the current source inverter is basically a force commutated one. It means we can switch on and switch off each phase irrespective of the load power factor. So, this is a force commutated CSI. So, we can say here it is force commutated, forced commutated. So, the nature of this IA, IB, IC will be quasi rectangular. Ideally, this should be quasi rectangular having a block of 120 degree, and we can define an angle gamma here, and we can add this 3. We have a pi by 2 here, theta r, and we can decide the phase of the current which is injected into the stator of the synchronous machine. And similarly, in the converter side, what we have here is this is the following, that we can apply a reference VR, and alpha is automatically controlled to give us the reference VR. We can apply, say for example, we can say that VR we want to be 200 volt or 300 volt, and depending upon the VR, alpha is generated to satisfy the reference VR. So, this is the power circuit diagram of a CSI fed synchronous motor drive. Now, we will do some analysis here. The question is this: it is a self controlled drive, and the performance of this drive will be similar to that of a DC drive. We ultimately, what we are doing here, we are feeding a DC voltage. Although we have a 3-phase AC supply, the output of the converter is a DC voltage, and the DC voltage is the input of the CSI. So, it is something like we can control the synchronous motor just like a DC machine. So, what we will do here, we will just write down a few equations in this case. Now, in this DC link, this is our DC link. So, we can say here that VR, the applied voltage, is equal to RDC into II plus VI. This is a equation, Kirchhoff's voltage equation, and we can multiply this equation by II. And so, if we multiply with II, we can say that VR into II, that is equal to RDC into II square plus VI into II. So, this is an interesting equation, and the CSI input power is VI into II. So, if we simplify this, we can do some mathematical rearrangement here. VI into II, that is equal to VR into II minus RDC into II square. Now, we assume that the synchronous machine, I mean the CSI, the current source inverter, is lossless, does not have any loss. So, what we can assume here is that the CSI does not have any loss. So, whatever is the input power here is going to the machine directly. There is no loss inside this CSI. So, if we assume this, we can say that that is equal to, this is the input power of the current source inverter, and that is equal to the power which is given to the machine. The machine is having a power factor of theta, cos theta. So, we can say that is equal to 3 into VA is the per phase voltage of the machine, into IA is the per phase current, into cos of the angle between VA and IA, that is theta. So, this actually is the power balance equation of the CSI fed drive, and from this equation we can derive an equivalent circuit which will show that the behavior of this machine is similar to that of a DC machine. So, this equivalent circuit derivation we will be discussing in the next lecture.